Just share my screen. Okay. So, we've been going through this course. We started with the brief introduction, then particle characterization, then tools, where we learnt about vectors and tensors and simulation methods. And then we looked at statics and slow flows. In those flows, the whole flow is just dominated by friction between particles. And now we have gone to the other extreme where you have rapid flows, and here the flow is dominated by interparticle collisions. And one way of studying these kinds of flows is using kinetic theory. And what we are doing right now is some examples using kinetic theory, which is this kinetic theory proposed by Half. And the example that we are looking at is steady shear flow in zero gravity. So you have two plates separated by a distance h, and top plate is moving with a velocity u. The bottom plate is got a zero velocity, and then the walls are absorbing. So the temperature or the fluctuation velocity at the walls is zero. And what we had already seen is that here we have the mean velocity ux depends only on y. If we solve the momentum balance equation, we see the shear stress is a constant, we're calling it tau zero. The pressure is a constant, we're calling it T0. And then we are left with the energy balance equation. This is the viscous dissipation, this is the conduction, and this is the loss due to inelastic collisions. And these are the boundary conditions. So in the last class, we started from this equation, which is the simplified energy balance equation. Here what we have done is we have substituted for, in here we have substituted for dux by dy and k and I, and then we get this. And we saw at the start that the two unknowns are s and square root of t. Since pressure is a constant, we can invert the pressure constitutive equation and get an expression for s as a function of the temperature. And then we can substitute that into this equation. Then you'll have one equation just in terms of temperature. And then further simplification happens if you put t to be just in terms of the fluctuation velocity v squared. If we substitute this, then we finally get a simple harmonic equation. d squared v by dy squared is just omega squared v. And this omega squared is given by this quantity, which is the ratio of shear stress to pressure. And these are all dimensionless constants. And these are also all dimensionless constants. Now we expect omega squared will be greater than 0 because this is the generation term, the energy generation term, and this is the energy loss term. So if you want a steady flow, this must always be larger than this. Otherwise, you will get zero flow. So with this, we were able to solve. The solution to that equation is just given by v is equal to b sine omega y. And what b is still unknown, but we know omega now is just pi by h. And once you put this, then you can get an expression for the ratio of shear stress to pressure as given by this. So if you are given the pressure, you can easily calculate the shear stress because everything else over here is known. Then this is just the fluctuation velocity. We also want the mean velocity ux. So we start with the stress constitutive equation. Tau xy is just viscosity into the velocity gradient. And then we substitute tau xy is tau 0, which we have already found out. Eta is given by this expression, which we can substitute here. And of course, S is equal to this, which we have used before. So we did all this. And we got the velocity gradient to be just given by this expression, where the velocity gradient is proportional to the fluctuation velocity. And then if you substitute for this using this expression, then you get a simple equation which you can integrate, and then applying the boundary conditions that velocity is 0 at the base and equal to u at the top plate, you will get essentially the two constants. One will, you'll get the full velocity field, and you'll also find out what is b, which is given by this. So with this, you are able to solve for everything. So now since b is known, now you know what is the fluctuation velocity in terms of known parameters, you know the mean velocity in terms of known parameters, and then you can find out what is the shear stress, and you can find out all the other things that you want to. Okay, so this is where we stopped, and now what I will do is I'll do a couple more examples using rapid flow. One is what happens if you have an isothermal shear flow. That is exactly the same problem here. And what I should mention is that, if supposing you put a Newtonian fluid in this system, for a Newtonian fluid, a shear flow will just give you a linear profile like this. But we are not getting a linear profile. I've purposely drawn this curve because you can see that the profile that we have got is this type of profile. So this is 1 minus cosine of. So obviously this profile is like a cosine curve, which is something like this. So this is our velocity profile here. It's far from being linear. And the reason that it's non-linear is because the temperature is varying. And because the temperature is varying, the viscosity is varying as you go from here to here. Okay. And so hence your velocity is not a linear profile. So now we'll do something where, supposing we assume that the temperature is constant, then what do we get? And what we'll show is that in fact the profile will be linear. Okay, so we'll do that, and then I'll talk a little bit about the first theory for granular flows, which was done in 1954. And that's a very simple theory, but it essentially agrees with all we have been doing from the kinetic theory. Okay. So any questions? If not, then I'll continue this. So I hope you can see this thing. So I'm going to start with this. So today we are in lecture number 25. And the date is 28/9/21. Okay, the example I want to do is even simpler than what we had done earlier, and that is steady isothermal flow between parallel plates at zero gravity. So there's no gravity force. So, essentially, the equations will remain the same. So the momentum balance will give us the x momentum balance gives us tau xy is equal to tau 0. Since this example is exactly the same as before, the only thing that is changed is that we are saying that T is a constant. So we are not giving the temperature boundary conditions, but T is a constant. So all the equations that we had done last time are the same, which is P is equal to P0. And then, of course, we have our energy balance equation, which remains the same as before, and that is just given by tau 0 into dux by dy So these are the equations that we got last time for steady flow between parallel plates at zero gravity. But now the only thing additional that we are doing is we are saying it's isothermal. If it is isothermal, then this term will go to zero. So this is the only change that we get from the previous problem that we had solved. Now, what we can say is that here essentially we have sorry. Yeah. So if we use the pressure constitutive relation, that is alpha rho bulk dt by S is equal to P0. Now, since temperature is constant, so since T is constant, this implies that S is constant. So for an isothermal system, your spacing between particles is going to remain a constant. So S is a constant. And we also know from the stress constitutive equation, if we substitute for the viscosity, this is eta 0 rho b d squared into square root of T by S into dux by dy is equal to tau 0. So you can see in this equation also, all these are obviously constant. Since it's isothermal, temperature is a constant. From this equation, we saw S is a constant and tau 0 is also a constant. So this implies that dux by dy is just equal to some constant C1. And we can immediately solve for the velocity profile is just C1y plus C2. And then, of course, the boundary conditions are that ux is equal to 0 at y equal to 0 and ux is equal to u at y equal to h. And this essentially gives us, if we substitute for this, we can get C1 and C2, and we will get And sometimes you can write this also as gamma dot into y, where gamma dot is just equal to u by h. So this essentially gives us a velocity profile. If we have this as y and this as x, then this profile of u is just like this. That there is a linear variation of the mean velocity with y if the granular temperature is constant. Now we can look at the energy balance. So here it is, and we can substitute for dux by dy, which is a constant. We are calling it as gamma dot. And then we can substitute also for the loss due to inelastic collisions. So, we know tau zero is given by these things. So we can, when we write for tau zero in terms of the velocity gradient, then what we have is eta 0 rho b d squared into square root of t by s, that is the viscosity, into the velocity gradient, so that you'll get dux by dy whole squared, minus the loss due to inelastic collisions, I0, 1 minus e squared rho b t raised to the power of 3 by 2 divided by s. And this is equal to 0. So this is exactly what we had solved earlier in the previous class. The only thing is that the conduction term, which has got the derivatives of temperature, is missing. So now this is a nice simple algebraic equation. And if we rearrange this, then you will see that you get this square root of temperature cancels with that to give you just temperature. And then if you take everything on the other side, then you just, what is nice is that first of all, of course, rho b cancels out, s cancels out, and t cancels out from here. So you just get one t over there. And so now you are just left with t is equal to eta into d squared. Here d is the particle diameter divided by I0 into 1 minus zeta 0 times d squared 1 minus e squared into so this is a really nice result, and in some sense it's a general result. And what it says is that if you have a shear flow without conduction, then your temperature is just proportional to your velocity gradient dux by dy whole square. And with this, we have completely solved the problem. We found the mean velocity to be given by this, and the temperature is given by this, but we know dux by dy is just u by h. So actually, if we want to write it in terms of all the quantities that are given to us, then this can be replaced by u squared divided by h squared. So this is your final result. But for many of the shear flows, we'll find that if we neglect conduction term, then this will always hold that temperature is proportional to the velocity gradient squared. So we can say this is a general result which is valid when these conditions are met. Okay, so now let me just go back in time a little bit. Now, one of the pioneers in this field of granular materials was someone called Bagnold. And he actually was posted as a military man in the desert in the Middle East, in Libya, working for the British Army, and his job was to keep really to just keep all the roads free of sand. So he had a truck which was a laboratory, and he was basically looking at how sand flows. And then he came back and became a professor in Cambridge University and continued his work on granular flows. And then he proposed some very nice, simple theory. And he also did a lot of experiments to show that the theory was valid. So he essentially he calculated the stress in a collisional regime. That is, the stress transfer is due to collision. But he based this on dimensional analysis. So I'll briefly go through his arguments, just so that we get a feel for why it's like this. Why do we get these kinds of results? So he considered that, let's suppose you have a shear flow like this, where just like in the previous example, let's say this is H and let's say this is U. So your velocity gradient, gamma dot, is just U divided by H. This we can say is the velocity gradient or the shear rate. And what he imagined is that, let's say he just imagined that there are many layers of particles. And what he thought was that let's just look at two layers of particles. So there's three layers, three particles here. And I've got three more particles which I can put over here. And so now what he imagined is that here you have these particles like this. And essentially what he imagined is that these particles, the top layer of particles is moving with the velocity v, and the lower particles are moving with a velocity v prime, which is less than v, because we have a velocity gradient like this. And he imagined that the separation between this is of the order of the particle diameter d. So basically his argument was that if you look at v minus v prime, then this is approximately equal to gamma dot into d. So that's the difference in the velocities is given by this. And then he said, okay, supposing you look at the change in collision when two particles collide. So change in momentum per collision. Then he said this is just equal to the mass of the particle times the velocity difference, which is equal to m into gamma dot d. So this is the change in the momentum per collision. And then the second thing that he mentioned is that if you imagine, then these particles, how many collisions will they be experiencing? So if you look at the number of collisions per unit time, then this is just going to be given by 1 divided by the square root, because the distance between the particles is d, and the difference in velocity is gamma dot d. So if you do d divided by gamma dot d, then the time will just come out to be, I'm sorry, the time will be gamma dot, and if you look at the number of collisions, it will be just 1 by the time, which is gamma dot. So I'll just write over here what I just mentioned here, that the time between two collisions is equal to just the velocity, the distance that is traveled is d divided by the difference in velocity, and this comes out to be 1 by gamma dot. So if this is the time between collisions, then the number of collisions per unit time will be inverse of that. Hence, that's why you get this is gamma dot. So that then you get force, which is nothing but the rate of change of momentum is equal to the change in momentum per collision, which is m into gamma dot d multiplied by the number of collisions per unit time. So this will give us the rate of change of momentum. That is what is force, the rate of change of momentum. And then your stress is just equal to force per area. And if we take the area to be just the particle diameter squared, then this is just equal to m to gamma dot d into gamma dot divided by the area, which is d squared. So if you simplify this out, so you see that the stress is just m gamma dot squared by d. So this is what you get. And here we are considering only one particle. Now if we write this mass of a particle in terms of its density, then this can be written as rho p into the volume. We can write it as just d cubed. So this is d cubed divided by d. So it will be just d squared into gamma dot. So now this is all considering one particle. Then for a collection of particles, this stress will also depend on how many particles there are per unit volume and so forth. So in general, what you will expect is that the shear stress will be given by rho p d squared some function of the volume fraction, solid volume fraction phi, gamma dot squared. So this is what is known as the Bagnol stress. So here let me write down phi is just the solid volume fraction this is known as the Bagnol stress equation. And of course, remember gamma dot is nothing but dux by dy. So what we actually get is that tau xy is proportional to dux by dy whole square. And for a Newtonian fluid, we have tau xy is proportional to. So this is the major difference. And the reason that this happens, we can try and understand why we get this type of dependence by essentially looking at the relationship between the half model and the Bagnol theory. Now, in the half model, the shear stress tau xy is equal to eta 0 rho b d squared square root of t by s dy. Now, for the case of no conduction, your temperature is simply given as, we just found this out, eta 0 t squared gamma dot squared, or d squared divided by I0 into 1 minus e squared times dux by dy whole squared. And so if we now substitute this in here, then you can clearly see that tau xy is just eta 0 rho b d squared. Now instead of this, I can essentially put in the constant over here, which is just eta 0 d squared divided by I0 into 1 minus e squared raised to the power of half, and then du by dux by dy raised to the power of squared raised to the power of half, which actually gives us the modulus of dux by dy times dux. So this implies that the half model is equal to the Bagnol theory for a case of no conduction. So these two are exactly identical to each other. Okay. So I should mention that this is validated by experiments. But if you actually look at it theoretically, then this will hold good only if the temperature is proportional to the velocity gradient. And really what we are finding if you look at this equation, this part is the viscosity. So tau xy is viscosity into dux by dy. And since temperature is proportional to velocity gradient squared, so that means that the viscosity is proportional to the absolute value of the velocity gradient. And that's why you get the shear stress is proportional to the velocity gradient squared. So this was just as a connection with something that has been there for a long time. And then finally, I want to do one more example, again using the half theory. So this is the last problem that I'll do for the kinetic theory part. So here is a case where I'm saying that there is gravity because it's gravity driven flow, but I want to neglect conduction. So let's suppose that conduction is not there. So this makes the energy balance equation very easy. And so this is my problem. Supposing I have a surface like this, inclined surface. Okay, and that surface is inclined at an angle. Let's call that angle as theta. Let's suppose that the granular material is flowing on this surface. So, it might be a long system, and we are looking at only the part in which the flow is fully developed and steady. And let's take this coordinate system where y is the distance from the free surface. Let's suppose that gravity is acting in the downward direction like this. Okay, and what we expect now, there'll be a flow something like this in this system. That there will be a nice unidirectional flow on this. Okay. So okay, so let me ask some questions to you all. Have you ever seen this kind of problem before for a fluid? Have you done the fluid flow problem for flow down an inclined plane?
Yes.
Yes, sir.
Yes, sir.
Everyone has done this.
Yes.
Does anyone remember what sort of profile you get?
Parabolic.
Exactly. So there is a for Newtonian fluids, we know the solution. And you get a parabolic profile. But we would like to do it for this case. And what are the assumptions we'll make over here? So the first thing is that we'll assume steady, fully developed flow. And so that means that our mean velocity has only one component, ux, and it depends only on y. And uy and uz are both 0. So this is what it is. Okay, so this is one assumption. The second assumption we'll make is that there is no conduction. So that in the energy balance equation, the conduction term will be put to 0. Okay. So these are the two major assumptions that we will make. And if you look at the boundary conditions, then what you have is that ux is equal to 0 at y equal to h. Let's call this distance as h. And then what is the boundary condition at y equal to 0?
Velocity u.
No. Think again. I don't know what is the velocity. So you imagine there's a plate, I'm pouring some water on the plate. I don't know what is the velocity. I want to calculate the velocity at the free surface. So what should be the boundary condition? So, if you look over here, what condition is satisfied? Does anyone remember? Free surface boundary condition?
Maximum velocity at the boundary.
Correct. The velocity is maximum, but more properly, if you talk in physical terms, then the condition is that the shear stress must be 0 at y equal to 0.
Yes, sir. Yes.
Correct? Because the air gives no shear resistance to the fluid as it's flowing. So that's why we can take this as a good approximation that the shear stress is 0. So at gas liquid interfaces, we usually will take this condition that shear stress is 0. So those are the two boundary conditions. Now, from the continuity equation, we'll see that all the terms are 0 except dux by tx, because uz and uy are 0. So you have this term, the continuity equation just becomes ux by du. And this one you can say is satisfied because since ux depends only on y, so this continuity equation is satisfied. Then let's look at the x momentum balance equation. Okay. I'm going to write it down. Do you remember this equation? Only for 2D I'm writing, not for the z term. Okay. So the left hand side is the inertial terms and the pressure and the stress terms and then the gravity. See, gravity is acting in the y direction. That's why this is a positive term there. And you have to take cos of theta into account. So if theta had been 0, then gravity would be acting in the y direction. But since theta is not 0, so then some component is acting in the y direction. But now, we can put red lines through everything. It's a steady flow, so this is 0. Dux by dx is 0, so this is 0. Uy is 0, so this is 0. There's no dependence on x, so this term will be 0. See, there's no dependence on x, so this term is 0. So you finally simplify to something very easy, and that is that 0 is equal to so this is your x momentum balance. You can do the same thing for the y momentum balance. I'll not do that. I won't write it all down, but you'll have a very similar equation, and if you do the simplification, you'll find out that it's just minus dp by dy plus rho b g sine theta. This is the y momentum balance. So essentially what it says is that the pressure as you go down, so the pressure will be 0 at the free surface, but then as you go down, the pressure will increase. Okay. And then the final thing that you have is the energy balance equation. And here, instead of writing the full thing, I just write down the terms that are non-zero. So this is the viscous dissipation term, and then the other term is just the loss due to inelastic collisions. So these are the three equations that you have. What I want to say, one thing, and I think you all know this is actually just a stress balance. So this is valid for all fluids. It's not dependent on whether this is a granular material or not. If it's water flowing, you'll have this. If it is polymer flowing, you'll have this. For all of them, it's the same. So there is no difference. Of course, this is only true for this equation. The energy balance is valid only for a granular material, but for the first two momentum balance equations are valid for everything. Now, if you just integrate these equations, because this is a constant, this is a constant, so you can just easily integrate it. And so if you integrate it, taking that both pressure and stress are 0, then what you will get is that the shear stress is just equal to minus rho b into g I made a mistake in writing these things down. This should have been interchanged it. This should be sine of theta, and this is cos of theta. Sorry. So both are increasing linearly, both are 0 at the free surface. And again, these are valid for any kind of fluid. Now, if we use the two conditions, one, we want to now solve for the velocity field, right? So we want to find out what is ux as a function of y. So we want this, we want to find out this. So how do we do it? Well, we know what is tau xy, and now we can substitute for tau xy using the constitutive relation. We know that from the constitutive equation for stress, we know that tau xy is just equal to the viscosity, which is eta 0 rho b d squared into square root of t by s. This is the viscosity into dux by dy. Okay, and what, since there is no conduction, the energy balance equation will give us we have seen this already. We know that the temperature is just equal to whole squared. So we've just done this. I mean, we were just sitting, just for the Bagnall thing, we did this. So essentially, just to repeat exactly what we have done, this is nothing but eta 0 rho b d squared by s, and then substitute for the temperature. So that is eta 0 d squared divided by re0 into 1 minus e squared raised to the power of half. Now, when we take the square root, we have to take the positive sign only. So even if du by dx is negative, as it is in this case, we have to take the positive sign. So we will take this as absolute value of dux by dy multiplied by dux by dy. So this is a constitutive relation. We had just derived this earlier. And what I'm going to do is I'll put everything, all the constants, into one function called f of phi. So this is equal to, let's say, f of phi into rho b squared, rho b d squared so this is nothing but the Bagnall stress equation. So we have done this the second time in this lecture, converting stress from half to Bagnall. But now what we can do is we can substitute for tau xy using the stress balance equation. So you have minus rho b g sine theta into y is equal to f into rho b d squared absolute value of dux by dy into dux by dy. And now you'll understand why I'm putting these absolute signs and so forth. Now the left hand side is a negative quantity, so the right hand side also must be negative. So that means that du by dx must be a negative quantity. And you know that because since y is going downward, so velocity reduces with y, so obviously dux by dy is negative in this coordinate system. So that means minus dux by dy is positive. So what we can write this as is, now of course rho b can cancel out. And then what we can write is minus dux by dy, which is a positive quantity, whole squared, is equal to g sine of theta divided by f into d squared times y. And then what turns out is that if we take the square root, then you get du by dx is equal to minus some constant a into y raised to the power of half, where a is equal to g sine theta divided by f into d squared raised to the power of half. So here we have a very simple equation. And you can see now, since a is a positive quantity, obviously square root of y is positive. So dux by dy is negative. So if we integrate this, we'll get ux is just equal to minus 2/3 a into y raised to the power of 3 by 2 plus c1. And then if you apply the boundary condition that ux is equal to 0 at y equal to h, then you will get the expression for ux that is just equal to 2 by 3 into a h raised to the power of 3 by 2. So this is what it says. So this is known as the, again, it's called the Bagnold profile, because Bagnold was the first one to actually come up with this result. And you can see that this is not a parabolic profile. For a Newtonian fluid, you would have had a parabolic. This is going as, instead of y squared, you have y raised to the power of 3 by 2. So this is the unique thing about the granular material, that you don't get a parabolic profile, but here you get a Bagnold profile. And this profile comes, you get this whether it is using half theory or whether you use Bagnold theory. But if you use half theory, then you have to assume that there is no conduction to get this profile. Okay. Okay. So I think with that we can end this lecture, and also I'm going to stop on the rapid flows, and then we'll go on to another topic of dense flows in the next class. Also remember that in the next class on Thursday we have a short quiz which will be held in the class itself, and details of that are in the announcement that I had put up. So thank you, and I'll see you all on Thursday.